Okay, we were a little late doing this. We've already researched the first part. If you're coming with us, we went on to the internet and researched fumotoxin and phosphine gas, and on KSL we did the bottom two of your notes about the two girls that were killed with the fumotoxin. We also did the phase diagram. You'll need to get that from somebody. We are now doing the ideal gas law and identifying what each part is. So if you've missed the first part, I'll try and catch it in fifth period, so you can flip to fifth period if you want to. So we've got pressure in atmospheres, volume in liters, and the ATM, 1.3 kilopascals, and 600 torr in millimeters mercury can be used to convert into atmospheres. It needs to be that. We also are given, and now this isn't working. Great. We also are given a constant R. And R is 0.0821 atmospheres times liters divided by mole Kelvin. And that's a constant. It's always the same. We also have T, temperature, which is given in Kelvin. And Kelvin is just Celsius plus 273. You'll notice there's no degree sign here. We don't use degree sign with Kelvin. I see you're writing furiously, so I'll let you keep writing for a second, and then we'll talk some more. Okay, moving on. Maybe. Okay, we also have temperature, besides the absolute temperature, Kelvin. We want to be able to convert between Celsius and Fahrenheit. And this over here on the right, or left of your screen, is the conversion between Celsius and Kelvin. Or Celsius and Fahrenheit, sorry, not Kelvin. So you can put that somewhere for you so you have it. There's not nearly a spot there. So degrees Celsius equals 5/9 times of Fahrenheit minus 32. Got it? So Celsius equals 5/9 times Fahrenheit minus 32 in parentheses. I don't know why it's not even letting me. Okay, whoa. Okay, so STP is the next thing we need to talk about, really. Okay. On STP here, we've got 0 degrees Celsius as standard temperature, or 273.15 Kelvin. Anytime we use any gas law, we want to change the temperature into Kelvin, because we want an absolute scale that doesn't have any negatives and it doesn't have any zeros. Otherwise, our equations are going to go wacko. We also want to be in atmospheres. Remember, these are all equal to atmospheres, so we can use them to convert if we need. So standard temperature and pressure, anytime you see STP, it's 0 degrees Celsius, which is 273.15 Kelvin, and 1 atmosphere. And I've put in red the ones that we really need to remember. Kilopascals. Kilopascals. It's a unit of pressure. It's just like inches, mercury. It's a way of pressure. Okay, so the ideal gas law we can take and we can, to solve it for R. So if we solve it for R and we say this is one set of data on the left here and one set of data on the right, then we can set those equal to each other. And if we set them equal to each other, we get what's known as the combined gas law. P1 V1 divided by N1 T1 equals P2 V2 divided by N2 T2. Okay, a lot of times we drop the n's. Okay, the n's will drop out because we don't play with the number of moles very often. Okay, a lot of times it becomes this. That's how we'll use it the most. So if you'll circle the n's on, if you put the n's in there, just remember that they're often not there. Okay, so we're going to play with some syringes for a minute. They don't have needles. Here, you can play with that one. Okay, I want you to just play with it for a minute, and we're going to talk about it. You guys back here, I'm going to make some more really quickly. Will you guys do what I did and just pull the plug off and open this up, and I'll do really quickly. Yep. I'm going to give you a little balloon to go inside of it. I was like, why? Okay, I'm going to have you put this back in, the syringe part, and then put the plunger in halfway, and then put the a little bit less. Then put the cap back on and then play with it. I could make it pink. I'll see if it'll fit. I might have made it too big. Okay, yeah, play with it. Play, play. Okay, tell me what's happening. Give me a law. It's hard to push down. What happens to the balloon when you push down? It gets squishy. If it gets squishy, what happens? So I push down, what happens to the balloon? Gets smaller. If I pull out, what happens to the balloon? Gets bigger. So what's happening here? What are you doing when you pull the syringe in and out? What are you changing? Pressure. So as pressure increases, what happens to the volume of the balloon? It decreases. And as pressure decreases, what happens to the volume of the balloon? It increases. Okay. So I'm going to let you play with this for a few more minutes, and then we're going to put them away. I know, sad day. You like to play, I know. Okay, try this one. Mm-hmm. Is anybody's balloon not working? Not getting big or small? Some of them have been used a lot, and they get, the latex gets a little bad after a while. These balloons are so old. Yeah, bop. They're stuck to each other because the inners are stuck. So is everybody's balloon okay? Doing okay? Okay, let's talk about this. Then I'll come around and collect. So we came up with the thing that as pressure increased, volume decreased. And as volume, whoa-ho, go find your parts. This is known as Boyle's law. Okay, looks like I'm going to have to Quick. Okay, make sure that you take the end off and make sure that the plunger is halfway down. Yeah, halfway down, and then put it back on. Okay? Because then you can increase it or decrease it. Okay, I'm going to come around and collect. Then we can focus again. Okay, did you have one?
Yeah, you already grabbed mine.
Okay. Thank you. Oh, darn. Okay.
Oh, now they know I talk.
Why is mine so big?
Okay, I don't know. Okay, so we are doing Boyle's Law. Boyle's Law, I put a tea kettle up there because I want to remember it has to do with temperature. And temperature is held constant. And because temperature is held constant, we take the combined law and we drop out temperature. Because temperature is constant. And this becomes Boyle's Law. Okay, so think temperature held constant, Boyle's Law. Write that down. That's next law. I'm going to go through these laws pretty quick. These next laws, they all are the ideal gas law. We just put them together, solve for R, and then we drop out what we don't need anymore, what remains constant. Combined gas law is P1V1 divided by T1 equals P2V2 divided by T2. You could also have N1 and N2 on the bottom. Okay, whoops, Charles' law. Now, poor Charles never will be king because he got passed over, but he's under a lot of pressure, right? The royal family's under a lot of pressure. So you say pressure's held constant, okay? Pressure's held constant helps me to think of Prince Charles because he's under constant pressure. And again, pressure drops out. Okay, so on this one, we take the combined gas law, and since we didn't get pressure or pressure was held constant, it drops out. Okay, N could be there again, but usually isn't. Then we get Gay-Lussac's. Okay, it's two guys. I think of it as sucks at the end because sucks, you suck up a straw and its volume. So when we look at volume held constant, volume drops out this time, and we get Gay-Lussac's law, which is about pressure versus temperature. So go ahead and write that down under Gay-Lussac's law. So you've got that law. Tyler, you got that written down? So this is Gay-Lussac's law. Everybody got this down? You're going to want them. Okay, stay with me. Come on. Focus, children. Yes. I called you a children when you act like a children. When you act like a young adult, I will call you that. When you act like... Okay. Graham's law is a little bit different. Graham's law is about how fast gases move. So Graham's law takes the equation Ke equals 1/2, and I don't think it's going to write mv squared. Well, there it went. It's just a little late. So it takes that equation and it sets it equal, the kinetic energy equal to each other. And it calls the m and the velocity 1 on one side and 2 on the other side, or a and b, and you solve for it. So this is the velocity or the rate, and this is the mass, the molecular mass of the substance. So I have to put the square root so I can get it out of being squared on the rate side. And this basically just says how fast gases are compared to each other. So I have to have two gases that I'm comparing to each other. We're going to do a lab in which we put hydrochloric acid on one, and we're going to put, Kyler, please put it away, or it's mine. Thank you. And we're going to put ammonia on the other side, and we're going to see which one goes faster. When they go together, they make a solid, which is ammonium chloride in the center. And that ammonium chloride, you can see the bandwidth right here on the bottom is pretty big. We want to catch it when it first forms. And then we can get the ratio of how far they went. Okay, let's make sure we turn off those computers and shut them down right now, please. I appreciate that. Put the lids down. The next one, man, I wish I was around when this guy got credit for this law. I call it Dalton's Doe law on purpose because it's like, how could you not figure that out? This is just dumb. All the pressure total is equal to all the little parts. Add it up. So if you want the total pressure, just add up all the pressures of all the little parts and you'll get the pressure total. Duh, right? We use it this way. So we use it where we say the pressure total is equal to dry gas plus the water. In lab, we do it this way. If we have a pressure total, that would be like the pressure in the room, and then I bubble the gas through water, I need to know the pressure of the water that went to vapor. So I have to subtract from the pressure in the room the pressure of the water to get the pressure of the dry gas. That's how we use it in lab. We sometimes use it this way if we're putting more gases into a container at the top, but mostly the bottom way. So you have a little box down at the bottom.
Pressure, temperature, and volume. If we imagine holding temperature constant and raise pressure up, notice that volume would decrease. This is the relationship Boyle came up with. Pressure is related to 1 over volume. If we hold volume constant and increase the temperature, we notice the pressure will go up. If we hold pressure constant and raise up volume, temperature goes up. This will hopefully help you remember these relationships.
Okay, so what I'm going to do is just, you've written this on the bottom. This is just a real quick, easy way. If you hold pressure constant, you just put your finger on the P. And then if you move volume up, temperature will go up with it. If you move volume down, temperature will go down with it, as long as you hold your finger on the P. If you hold your finger on the T and press hard on the table so you can just wiggle the paper, you can move the V up. As volume goes up, what happens to pressure? Goes down. If I move volume down, what happens to pressure? Goes up. Okay, what if I have volume constant? What happens? Pressure goes down. What happens? Temperature goes down. If pressure goes up, temperature goes up. This is a really quick, easy way to answer questions on the ACT and the ACT. Yes? This is proportional to. Okay? Stay with me, guys. We're going to keep trying to move forward. For some reason, it doesn't want to move forward because I'm somewhere else. Okay, so this sort of just goes through that. This is the first problem set. You should have this on the back side. Really quickly look on the back side. We're going to do this together. So you have a problem of back side of the first page. Everybody got it with me? We're just going to go to the bottom of that page, and we'll stop for today. Okay? So up here, we've been given pressure, temperature, and we're trying to find the other pressure. Whose law? What's being held constant? Volume. So if volume is being held constant, whose law? The sucky one. Okay, so it should be Gay-Lussac's. Okay, so go ahead and put Gay-Lussac's. Back of the first page. Okay, what is the formula of Gay-Lussac's? P1 divided by T1 equals P2 divided by T2. Yep. So now what I'm going to do is I'm going to put everything in, right? Or do I need to do something first? What did I tell you about gas laws? Everything has to be what? The temperatures always have to be in Kelvin. They cannot be in Celsius. So how do I get these Celsius into Kelvin? Add 273.15. So I've done it for you here. Just go ahead and put the work down and show what to get your answer. So I like to rearrange it first, like right here, and then put stuff in. If that confuses you, put the numbers in first, and then rearrange it to solve for what you don't have. Whatever's easier for you. Okay? We're going to do one more problem set. P2 is what you're trying to find. Okay, so most of these gas laws are basically story problems. You have to pull out what each one is. So as you come to the first temperature, call it T1. As you come to the first pressure, call it P1. Make sure they're tied together, though. Sometimes they give you a pressure weird. Everybody got this? We need to add 273.15 to each of the temperatures to get these new temperatures down here. So 273.15. Okay, so here's the next problem. Here we're given this. Now this one did not tell me what each one is, so as I come through, a beginning pressure of P1. This, and I would write it down. P1 is equal to 2.5 atmospheres. A volume of V1, 27.3 liters. If the volume is increased to V2, 75.8 liters, what is the new pressure? Right? So that's P2. I'm solving for P2. I've got volume and I've got pressure. What's being held constant?
Temperature.
Temperature. Whose law? Boyle's. Boyle's has to do with temperature. So what's the name of the law? It's Boyle's. What's the formula for Boyle's law? P1V1 equals P2V2. These ones just times together. And I messed that one up. That should be, doesn't really matter though, because it's cumulative. Yeah, that word. Anyway, yes, commutative. Okay, so all we have to do is plug in. We're solving for P2, so we're going to divide both sides by V2. So when we do that, we get this. We didn't have to convert anything because it didn't have temperature. I like Boyle's law because I don't have to deal with the temperature. All the others I have to deal with temperature, and I have to convert it to Kelvin. So add 273 to all your temperatures before you plot it in. Okay, final answer, 0.9 atmospheres. So my volume went up and my pressure went down. So PTV, I was holding temperature constant, volume went down, or volume went up, pressure went down. Okay. Good morning. Okay, going on. So I know it says day 2, but we're in a little bit of a rush, so we're going to go right into it. It's not real hard. This first part, I am going to just go through. I said on your thing, wait until I give you the shortened one. So this is the fast version, or the long version. Okay, we're talking about kinetic theories, which has to do with how many times gases hit the walls and how they move. So here was the postulates. Gases consist of tiny particles, atoms, or molecules. These particles are so small in comparison to the distance between them that the volume size of the individual particles can be assumed to be negligible or zero. The particles are in constant random motion colliding with the walls of the container. These collisions with the walls of the container cause the pressure exerted by the gas. Collisions with each other are elastic. The particles are assumed to not attract or repel each other. And number 5, the average kinetic energy of the particles is directly proportional to the Kelvin temperature of the gas. Okay, so I call it the toddler rules. And this is what you need to write down. There are 5 toddler rules because toddlers are considered anybody under 5, right? Okay, so they are particles in an ideal gas. That's what it's about, is an ideal gas. Number 1, they have no volume. Toddlers are considered small and can sit on your lap, don't have to pay for a chair. Okay? They have elastic collisions. As long as nobody's looking, they fall down a lot and they get themselves up a lot and they don't really care. If somebody's looking, then they'll cry. Yep, we're under kinetics. They are in constant straight line random motion. I call it squirrel. Okay? They see something, they want to go to it, they go, oh, and then they see something else and squirrel away. Straight line to get whatever else that caught their eye. They don't attract or repel each other. They love everybody. They think everybody is neat and they go right to you and say, oh, it's cool. It was sort of awkward for me when my kids were really young because it was like they were just starting to talk like 2, and we hadn't been around very many different cultures at that point. And we went to the grocery store and there was a lady of color there and she says, Mommy, how come she didn't wash? I'm like, oh, no. God made her that way, sweetheart. It's okay. and it was really, really hard. But she didn't care that, she was, but then she went up to another person that had tattoos and dreadlocks and it was really scary looking to me. I was a little bit repelled. She went up and said, how come you have dangly jewelry all over you? They just didn't care. They just, They're okay. They're attracted, not repelled, retracted. Average kinetic energy. They want to go outside when it's warm. They want to be active. They want to move, move, move when it's warm outside. When it's cold inside, they'd rather have their blankie and watching Disney movies. They don't want to move very much. Okay? They usually want to watch the same Disney movie over and over and over and over again. Okay, so these are the five toddler rules. I'm going to be bugging you about 5 toddler rules. I call them the toddler rules because there's 5 of them and you're under 5. They're ideal. Kinetics. It's just a way to remember it. It's just a way to remember it. I call them the toddler rules because these are
Kinetic is the toddler.
Yep. This is the ideal gas, toddler rules. So these are ideal. Okay? So get real. We're teenagers. We know that's not how life is. Get real, right? How are we different than the toddler rules? Oh, we judge people. We are attracted and repelled by people. We are. What else?
We have volume.
We do have volume. We take up space. If I come up to poor Kaylee right here and I sit and talk to her like this, she moves away. You know, there's man, give me my space. Don't get too close. Okay? Sorry, but it proved the point. Okay, what else? Oh, come on, don't tell me you haven't had driver's ed. Collisions are three things in which real gases are different from toddlers, right? Or from ideal gases. So we have real gases and we have ideal gases. Okay, so I really want my teenagers to act more like my toddlers because they're so sweet and so lovable. When can I get them to act like ideal? Summertime, right? What's happening in the summer? It's hot. No school, less pressure, right? And who do you get to hang out with? Your friends, who you want to. Okay, so low pressure, high temperature, and non-polar situation. In other words, I can choose who I hang out with. Okay, so write these down so you know them. So how can I get real gases to act more ideal? Give them low pressure, put them in high temperatures where they can go out and do swimming and chill. Not really chill, but roast. And in non-polar atmosphere, I can choose who I want to be around. Okay, I'm going to buzz through the slides really quickly. Did everybody get these ones down?
Not yet.
Not yet? And then we're going to go right into working into your daily work. The daily work that I'm giving you today will also have time to work in class next time, but we are going to get daily work 2 next time. So I'm not going to give you a lot of lecture next time. We're just going to talk a little bit. We'll have a quiz at the beginning of the period, and then go into the working, so I can actually get around and help you if you're having problems with the math. Okay? All right, so characteristics of gas, we should know. They fill a container. You'll notice my little stink bug over here goes off every once in a while, and you get a smell throughout the room. Okay? They have random motion. Yeah, it's a whoosh, yeah. I call it a stink bug. It's a Febreze thing. Yeah, it goes off every once in a while, and you all of a sudden get a smell. No. Okay, gases are fluid, like liquids. So just like the phosphine gas, it will flow to the lowest, the heaviest gases will flow to the lowest areas. Okay, they have no attraction, they sort of flow over each other. They have very low densities. There's a very few amount in large amount of space. So we're looking more like this at the top. Some characteristics. We can compress gas. So why is it bad if I have gas in my brake line?
In your what line? It won't compress.
Because gas can compress, and so what is in your brake line? They put fluid in your brake line. If you have air in your brake line, it can compress, and you can press as much as you want, and it's not going to close those calipers to make your brake and so you can press and press and press, and nothing happens. That's bad. Okay. Gases undergo diffusion and effusion. Now this is a difference. Effusion is like what's happening with my stink bug up here. It lets it go and it diffuses through the whole room. So I could put a piece of, put some chemical on a paper here and let it diffuse through the whole room, like butyric acid that smells like barf. And everybody would smell it right away. Okay? Effusion is what they use. They put chemicals in the gas line It's a really strong sulfur smell. You know it as a smell for methane gas, but methane gas doesn't have a smell. They put it in so that we know when we have a leak. And that's when it effuses through a small hole. So diffuse through the room, effuse goes through a small hole. Okay? A random motion. So kinetic theory, basically, if I want to have the same volume, then I'm going to have to add more pressure if I've increased the temperature. If I want to have more volume, and I've got to increase the pressure or temperature and keep the pressure constant. So if I look at keeping the pressure constant and changing the number of moles, then I've got to change the volume. Okay, in a smaller container, things have less room to move around, right? Hi. In about 10 seconds. Okay? Okay, they hit the side of the container more often. This causes more pressure, right? The volume, as the volume decreases, when we push the syringe in, what happened? The pressure increased on the outside and our volume decreased. Here's a quiz. I got a balloon riddle here. I've got a white balloon and a red balloon. Right now, this is closed. Okay, this is a riddle. Which side is going to increase? Are they going to end up equal? Decide which one you think. This side is the white side. This side is the red side. I'm gonna open these up, and I'm gonna have somebody hold and play with each balloon. Okay, how many think it's A? A is gonna get bigger. How many think it's B? They're gonna be equal. How many think this one is gonna get bigger and this one will get smaller? C. Okay. I'm gonna flip this. No, I'm gonna make it this way. No, I'm gonna flip it. Okay, I want each of you to hold that. When I open it up, I just want you to play with the balloon. Okay, ready? I'm going to open that one, and I'm going to open that one. Okay, play with the balloon. Play with the balloon. Come on. Play with it. Play with it. Come on. Don't break it.
I don't break it.
Play with it. What's happening?
Why is it all going here?
What happened?
That got smaller.
It got smaller. Have you ever blown up a balloon?
Yeah.
When's it the hardest to blow it up? This has a lot more latex pressure pushing in on it than this does, because once you've blown it up a little bit, it's easy to blow up, right? That's what's happened here. Okay, so I'm going to go through the last little part real fast. We're almost done. Okay, so we already talked about that. The pressure on the outside's bigger. This is Avogadro. Isn't he just handsome? Jeez. Ugh. He sort of gives me the creeps, his eyes. Anyway, don't look at him. There we go. Avogadro did it with between V and N, and I forgot to put that on. This is Avogadro's law right here. You want to add that to the bottom. His law basically said 1 mole is equal to 6.02 times 10 to the 23rd molecules, which is equal to 22.4 liters of any gas. Of any gas. Now, what will change? No. No. If I have the same volume, it has the same number of molecules for any gas. What will be the same? Or what will change? Sorry. What changes? The mass. Because helium doesn't weigh as much as oxygen, doesn't weigh as much as nitrogen, right? So that's the only thing that'll change. It'll still take up the same volume, have the same pressure, have the same temperature. It'll be 22.4 liters. That is right here. This is the last part of our mole map, going up and down. Okay? And now we're on to practice, daily work. Assignment 1, let's work. Okay. Okay, so I've given you a place in your daily work to write down your given. Write it down as you read. This is pressure. This is temperature. If I get a temperature that's not in Celsius, change it right away to Kelvin so you don't mess up. So would you like to do the first one together so you can see? Okay, let's do the first one together. Okay, I'm going to project it. Okay, here we go. First one. If you don't have a calculator, you want to grab one because you definitely need one. Okay, as I'm reading through this, I want to make sure I'm writing down. No, you could probably do it with a general one, but okay, reading. Following with me. Here we go. I have moles. Moles are in. And a pressure. P1. I'm going to just put P1 because I don't know if there's more than one. And a volume. What is the temperature? So I'm looking for temperature. Ooh, whose law?
Oh, it's
Pervner.
what?
Ideal gas law, Pervner.
I thought they were.
Okay, what am I missing? I'm missing temperature, but I also am missing R. What was R? R was a constant. Who remembers what the constant was? 0.0821 atmospheres times liters divided by mole times Kelvin. Okay? Now my work over here, I'm solving for, what am I solving for? Temperature. So I like to rearrange it first. Like I said, you don't have to. So I'm going to divide both sides by NR. So PV divided by NR. And I just plug in. So plugging in, pressure, 28.48 atmospheres times volume, 87 liters, divided by N, 14 moles, times by R, 0.0821 atmospheres times liters divided by mole times Kelvin. So looking at that, atmospheres cancel, liters cancel, moles cancel, and I've got 1 over 1 Kelvin. What's your one question? Okay. Okay, plug it through. Plug it through your calculator.
So we gotta do 14 times 0.0821.
I personally, when I have these, if I have a simple calculator and it has a 1 over X button, so I don't screw up, I put the bottom in first. 14 times the 0.0821, hit enter, then do 1 over X and times through the top. If I have a simple calculator. Okay, nobody's got to tell fifth period what's going on with this for tomorrow. It's like I'm going to set it up.
Remember the bucket thing we did where the water,
Mm-hmm.
not even that water? Oh, yeah. I thought everything was supposed to be.
This is because the pressure on the balloon, the latex pressure coming in, is a lot higher here than it is here. It's harder to blow up a balloon right when you first start because of the pressure of the latex. That's why. Yeah, it just pushes it out.
Okay, but so what if there's enough pressure on the big balloon, like if somebody like held it tight enough?
If you could hold it all the way around, the problem is the latex is flexible.
Yeah.
And so, yeah, really. Anybody got an answer? I know what it should be.
So you just get
2 sig figs. 2 sig figs. 2200. Done.
How do you know when it needs to have two things? Yeah. I think
Whatever has the least amount. Least amount. Because we're multiplying or dividing. If we were adding or subtracting, it would be to the decimal place. Okay, so I'll help you pull this next one out, then you need to do your own. Here we go. My car has an eternal volume of this. Volume equals, I'll put V1, 4459 liters. If the sun heats up my car from a temperature of 10.9, so T1 equals 10.95 degrees Celsius. Okay, I know right away I need to add to that 273.15. So that is 0, 1, 4, 8, 2. Okay, yep. Because it has to be in Kelvin. Has to be in Kelvin. So then I go next on the temperature of this. So that's my second temperature, T2, 135.28 degrees Celsius. Again, 273.15. I'm adding to it before I forget. Okay, there's my second temperature. What will the pressure be in my car? And then it says assuming, so I'm looking for pressure 2, because pressure 1 was initially this. So initially my pressure was 730 millimeters mercury. Since I'm not in the ideal gas law, I don't have to change that pressure into atmospheres. I can leave it that way. I added 273 to their temperatures, get it into Kelvin. Okay, so this is my T1, and this is now my T2. Okay? All right, so whose law? What's held constant? The volume's held constant, so it's Gay-Lussac's. And so that's going to be P1 divided by T1 equals P2 divided by T2. And what am I looking for? P2. So I'm going to put P2 on the top here, and I'm solving. So I'm going to get P1 divided by T1 times by T2 on the top. Plug in. That's as far as I'm going to take you. Okay? Good luck. Yes?
How do you find out a constant?
This one doesn't have a constant. Well, what you mean, what is constant? This right here did not change. I can't change the volume of the car. It's going to stay the same, right? The volume of the balloon I could change. Volume of the car I can't. Unless I get inside and start hammering. Or I crush it from the outside, right? Okay, good luck.